everyone. It's great to see you all here, and welcome to the March edition of Rocky World's Discussions. We're excited to welcome Katherine Kleer from Caltech, who joins us today to continue this discussion series. As a reminder of etiquette, please use your full name, if possible, on your Zoom, and keep muted through the talk, and then turn your video on if possible when asking questions at the end. So I'll now hand it over to Katherine to talk to us about tidally-driven volcanism and mass loss at Jupiter's moon, Io.
All right, excellent. Let me just share my screen here. All right, does that look correct?
Yes.
Okay, great. Well, thank you very much for inviting me to give this talk. I'm excited to tell you guys about my favorite object in the solar system, which is Io. In putting together this talk, I recognize that this group is a mix of both solar system, maybe Earth, and also exoplanet folks, and I see Io come up quite a lot in the exoplanet literature. So I kind of had in mind as I was preparing this to cover a lot of, in particular, the observational signatures that we have of the volcanism and atmosphere on Io, with the kind of aim of maybe stimulating some ideas or discussion about how we could potentially detect similar signatures in systems around other stars. So just to set up a little bit of context, sorry, get my slides working. Our solar system, provides a kind of single, very detailed data point for understanding one example of how planetary systems can look, and moon systems as well. And so this is kind of the overview of the major moons in the solar system. And outside of Titan around Saturn and Triton around Neptune, the only four beyond those large moons that we have in the solar system to really study these complex processes that you only have on larger worlds are the 4 Galilean moons, right? So between these 6 objects, those are kind of the big data points we have for planet-like worlds that are satellites. So you can see from looking at these moons just how diverse they are. You can tell that just by their textures and their colors. Each one is dominated by a different set of processes and gives us kind of a single data point for understanding how moons and satellite systems in general form and evolve, and what the different kind of end members can look like. Within the Galilean satellites, there's a spectrum of both composition and activity. So Io, the leftmost here, is the most volcanically active object.
I'm sorry, Katherine, to interrupt you. I don't think we're seeing your slides properly.
Oh, really?
Okay. Yeah, I'm seeing a figure of tidal heating rates in 3 maps. I don't think it's the first.
Oh, really?
I see the slides, so I don't know if it's on your end.
You see them? Oh, okay. Maybe it's on my end. Does everyone else see them?
You should be looking at a picture of the 4 Galilean moons right now.
Okay.
That's what
Okay, I think it's on my end, but then I'm sorry to interrupt. We can.
No problem. Okay, yeah, feel free to interrupt if there's more issues with slides, and we can try to troubleshoot. Okay, so looking across the 4 Galilean moons from left to right here, we have Io, Europa, Ganymede, and Callisto. These are progressing with distance from Jupiter, and they show a spectrum of heat flow, geological activity, and surface age, with Callisto being kind of this end member, non-geologically active object that has just been accumulating craters over the age of the solar system. Io is the extreme opposite example of that. It's got a very young surface. It's very geologically active. And we also see a spectrum of density that corresponds to a spectrum in ice to rock ratio, where the inner two Io and Europa are basically rocky objects, and Ganymede and Callisto are about 50-50 ice and rock. And there's still some debate about how much of that is a formational feature and how much is an evolutionary feature. But focusing in on Io, so its volcanism and heat flow are driven by tidal heating, which I have a slide about shortly. But just to, again, put it in the context of its neighbors, the other three large moons of Jupiter are these what are called icy ocean worlds. They have ice shells with oceans underneath. Io, in contrast, has a rock shell and a silicate mantle, which in this diagram is shown as a magma ocean. We now know it doesn't have a magma ocean, but certainly has some sort of melt and potentially a partial melt layer interior. So this tidal heating that melts Io's interior powers its volcanism. This volcanism outgasses specific species into Io's atmosphere. Every spacecraft that has flown by the Jupiter system has viewed these massive volcanic plumes on Io. You can see in this image just how high that plume goes relative to the radius of Io itself. It's a really substantial fraction of the size of the whole moon. That material then goes out to populate a whole system of plasma and neutral material that orbits Jupiter. And so you can study the material coming off of Io by looking at these plasmas and neutrals, as well as just kind of Io itself. So these themes I've covered in the introduction are basically going to be the themes of the talk. I've divided it up into 3 parts. I'll start by talking about the specific influence of tides as a heating process on the features we see in Io's volcanism. I'll then talk about Io's volcanic gases, what they're made of, and also what their fate is in terms of becoming ionized and forming these large-scale structures. And then finally, trying to understand how these processes have evolved over the entire age of Io. Okay, so starting with the tidal influence on Io's volcanism, a very quick reminder of tides. Tidal heating, the tidal heating in Io occurs because it's in an orbital resonance with Europa and Ganymede. That orbital resonance means that the moons encounter one another at the same places from orbit to orbit, so their mutual gravitational influence adds up coherently. This results in their eccentric orbits. And the eccentric orbit is what causes the tidal heating. Because Io is experiencing a time-varying gravitational field of Jupiter due to its eccentric orbit, its shape is actually changing every orbit, and that orbit is less than 2 days. Those shape changes generate friction in the mantle at a level that is sufficient to melt the mantle. And melted mantle is simply magma. And so that extrudes out onto the surface and gives us these observable signatures that we can use to connect what we see on the surface to what's going on in the interior. Io is the laboratory that we use to study the process of tidal heating because it is the place where this interior process manifests so clearly in surface signatures. However, tidal heating is a fairly universal phenomenon among the moons in the solar system. So here in red are the objects that are currently in orbital resonances or heated by obliquity tides. And then the blue are those that are thought to have passed through orbital resonances in the past. So this is a process that has affected nearly all major solar system moons and appears to be active on exoplanets as well, based on the orbits that we see them in. So a question that I have been interested in for a long time is, when we look at Io's volcanoes, what features of those volcanoes are actually linked to the fact that they're being powered by tidal heating and not by any other heating mechanism? So you could imagine looking for the influence of tides on Io's volcanism in a few ways. Tides should produce a specific spatial distribution of volcanoes. It should produce volcanoes that vary on periodic timescales. I shouldn't say should. They might be expected to, based on the periodicities and the spatial distribution of the energy input. So you might expect periodic volcanoes on a diurnal or longer timescale. And finally, you might expect that because tidal stresses have a specific orientation as a function of time of day on the surface, that you might see that reflected in the morphology of the volcanoes. So I'm going to start with point 1. I'm going to spend the most time on that because that's the one that's been studied quite extensively in the Io literature. So although we understand, in general that tides are providing the heat, the power Io's volcanism, we don't know yet what the actual heat production and transport looks like within Io's mantle. So for example, we don't know whether the dissipation is happening deep in the mantle, which requires then the melt to get through the entire mantle to the surface, or whether it's just happening in a shallow layer. And we don't have a good sense of how interconnected that melt is. So when we put together this diagram, we had these 4 different plausible quadrants. You may have seen a really neat result that came out from Juno quite recently. They used gravity data to show that there is no magma ocean on Io, which means that we don't have magma oceans in the solar system today. So this is kind of interesting from the perspective of thinking about the potential prevalence of magma oceans on other worlds. But still, we don't understand, where we are between these other quadrants, where the dissipation is occurring, and how the heat is being transported. One way that you can answer this question potentially is by looking at the spatial distribution of the surface heat flow. So if the heat is coming from the deep mantle versus the shallow layer, which we label the asthenosphere, you should expect the surface heat flow to follow quite different spatial distributions. So these are predictions from tidal heating models. They assume purely radial heat transport, which is an important caveat that I will come back to later. But you can see that they show these kind of degree 2 and degree 4 spherical harmonic components and predict quite different distributions of heat flow and therefore volcanism from equator to pole, and also as a function of longitude. But in order to really get the patterns of Io's volcanism, both in space and time, as I'll talk about in a little bit, we need a big statistically meaningful database of Io's volcanism over time. So spacecraft missions, Voyager, Galileo, and now Juno give us a tremendous amount of data in relatively short windows of time during the flybys of Io, and those have given us some significant data sets. I have additionally been using observations from telescopes, in particular on Mauna Kea, over about a 10-year period of time now to cover a longer time baseline. So we're not as sensitive to small volcanoes as the spacecraft, but we can cover consistently a long time baseline to build up this statistical sample. This is what Io looks like to Keck. These are 6 images just in 6 different filters, basically almost at the same moment in time. And at the short wavelengths, you're mainly seeing reflected light off of the disk. As you get to the long wavelengths to the right there, now you're seeing those little bright spots that are thermal emission from the individual volcanoes. Okay, so we've done this over many hundreds of nights. This is a small subset of the data at this point. And you can see these little hotspots on the disk. We pick out where they are, their latitude and longitude, as well as measuring their brightness. And then we can look at over time, look for statistical trends. So this animation, yeah, it's playing now, is showing over the first 5 years of the study where and how bright we were observing these hotspots, they're called. And you can see first that there's quite some variety in temporal patterns for individual hotspots. Some of them kind of flash on and off. Some, like the one near 30 degrees there, are pretty persistent, and others are close to periodic. There's one like that near 300 degrees. So for the purposes of the spatial distribution, it's really just the sum over time from this that we want. And this is what that plot looks like, just all of those detections kind of summed over the time axis. And we can compare this to Galileo as well as we do here. So this is the distribution of hotspots observed by the Galileo mission compared to our telescope data. And we're working on now incorporating the new Juno data into this. So you look at these spatial distributions, and I think the first thing that pops out at you is that they look pretty random. They don't follow really clear and specific spatial distributions. There's probably one exception to this that I find fairly convincing, which is that they're roughly clustered into 2 hemispheres, the hemisphere centered on 90 and the hemisphere centered on 270. Those are the leading and trailing hemispheres in Io's orbit. So Io is tidally locked. So the leading and trailing is the front and back hemispheres in its orbit. and the volcanoes are clustered into there. So you're kind of getting some signal in this degree two spherical harmonic term. If I overplot these on top of the tidal heating models, you again see that there's not a great correspondence. The color scheme is different from the last one I showed you, but red is more heat flow and therefore where more volcanoes might be expected. And you can see, I think this figure highlights even a little better the clustering into the two hemispheres, as well as the prevalence for volcanoes to occur at a couple specific longitudes that are spaced like that degree 4 spherical harmonic term, but it's not, doesn't extend to the other hemisphere. So, you know, there's some imprint of the pattern of tidal heating in the interior is coming out on the surface expression, but it is not extensive. And, you know, I think the reason that we're coming to understand for this is that some process is erasing the pattern at which the heat is being deposited in the interior between the interior and the surface, right? So, I said a few minutes ago that these models assume purely radial heat transport. And so if you have significant convection or significant lateral heat transport, you can start to erase these patterns. And also volcanoes are very complicated. You don't just sort of take heat and transmit it to the surface, and that's exactly where the volcano occurs. There are many geological controls on this that have nothing to do with tides. So I also wanted to show a plot if you were trying to visualize what these patterns might look like on an exoplanet, for example. I've now at least removed one of the spatial axes. So this is the fraction of either the number of volcanoes or the brightness of volcanoes versus longitude and 30-degree longitude bins. So this is just to show that looking at the actual heat flow, for example, there's about a factor of 2 actual spatial variation in heat flow if you were looking at a hemisphere averaged number. So coming back to this plot, you know, I think that what we're learning is that, you know, Io doesn't fall simply into one of these quadrants, that in fact the situation is more complicated, and we need models that account for better fluid flow in the interior. But also we may be learning that the geological controls on the volcanoes are outweighing the spatial pattern that we see. Or not that we see, that should be present in the energy dissipation. So we have a couple other features that we might look for. What about the timing of volcanoes? Because the tidal stresses vary with the orbit, you might expect to see either diurnal or longer timescale variations in the volcanoes. The plot that's on the top here, I tried to just sum together all of the thermal emission on Io over a period of several years and just look at globally like what the time variability patterns are. And you see that there's about a factor of 10 variability in just the overall thermal emission, specifically at 4 microns, which is the wavelength where we make the majority of the observations. So there's quite a lot of stochastic variability, but you may, in looking at this, also see some hint of a periodicity. It's not a perfect periodicity, but it may be kind of close to periodic. And so that variability, some of it's driven by just huge stochastic outburst events, they're called. But some of that is also driven by this one volcano, Loki Patera, that makes up something like 15% of Io's total heat flow. So Io has over 400 volcanoes on its surface, and there's one that makes up 10 to 15% of its heat flow. And that one does exhibit periodicity on a time scale of about 460 days. In this paper, we show, so here the points, the colored points are the brightness of this volcano, Loki Patera, over time, and the curve is Io's eccentricity. So we make an argument that there's some weak evidence that actually this volcano is tracking Io's changing orbital eccentricity. So this is like longer time scale, like 1.5 year time scale variations in Io's orbital eccentricity. But we looked for features like this in all the other volcanoes, and this is the only one that we found, and it's kind of just suggestive evidence. So it's certainly not tides are not the controlling influence, again, in how the volcanoes are progressing. And what about orientation? So on the upper left here is an animation showing the tidal stresses. You can't really see the little arrows, but red is where the stresses are extensional and blue is where they're compressional over the course of a single orbit. And the main point is that when the stresses are highest for a given point on the surface, they're oriented in a particular way. So that means that you could potentially imprint that orientation on the volcanic feature. On the lower right is a map of Io with what looks kind of like a little vector field for the orientation of all the volcanoes. And my student in my group, Tina Seeger, is looking at whether there's any correlation between the orientation of the volcanoes and the stresses on the surface. And that project is still in progress, but so far, in keeping with the theme of this section of the talk, we're not seeing a correlation between these two things. So I would say collectively, all these pieces of evidence are pointing to Io's volcanoes, the specific aspects of them being controlled by local and geological processes rather than actually imprinting any effective tides. So at the end of each section, I'm kind of collecting open questions, potentially things that we could discuss at the end of the talk. So the first one, which we're working on, but I would say is still unanswered, is how does Io's volcanism differ from how it might be if the heat source were something other than tides? I'd say we still don't know where the magma is generated, where and how it's stored in the mantle, and how it's transported within the interior. And finally, based on this result of Juno that Io doesn't have a magma ocean, are there circumstances in which tides can produce magma oceans? It's not obvious that this has to be the case, as when you have a small amount of melting in a mantle, that melting will just occur at the boundaries of grains and is not extracted very efficiently. But as you increase the fraction of melting, you start to extract that melt pretty efficiently. And so if you want to have a magma ocean somewhere, you need to be producing the melt faster than you can extract the melt. And I would say it's not obvious that this should be the case anywhere. Okay, so I want to now briefly talk about Io's volcanic gases, and this part in particular is kind of a survey of observational signatures in different ways that different, I guess, reservoirs that Io's volcanic gases end up in and how we observe them. So briefly, Io's atmosphere is dominated by SO2. It's very much the imprint of volcanism on the atmosphere. So that's the main constituent. There are also photochemical products of SO2. And then we see NaCl and KCl, which are outgassed from the volcanoes. So there's no water and there's no carbon dioxide on Io. Why that's the case is still a debated question. But sulfur is the primary volatile forming element on Io. So the SO2 is outgassed from the volcanoes. You're also close to the sublimation temperature of SO2 at Io, so you have an equilibrium between SO2 frost on the surface and SO2 gas in the atmosphere. So the stuff that passes through the atmosphere reservoir will recycle back into the interior eventually, but while it passes through the atmosphere, it undergoes these complex interactions with charged particles orbiting Jupiter, ions and electrons, which ultimately actually come from the same volcanic products that then get ionized. They come back around, they continue to ionize Io's upper atmosphere, and you lose all of this material in both neutral state and charged state, and some of the charged particles recombine. And then you end up with these large, both plasma and neutral structures. So in the upper left, it's just a schematic of what's called the plasma torus of plasma around Jupiter, sourced from Io's volcanic products. And then the images that are mainly making up this slide are all in sodium emissions. So the scales are at the bottom here. So from a scale of tens of Jupiter radii out to 1,000 Jupiter radii, you can see these massive sodium structures that are sourced from the NaCl that's coming from Io's volcanoes. These are very bright. You can see these observations come from the 90s. We've been able to observe these well for a long time. So the neutral particles from Io extend very far, and the dust that's come off of Io's volcanoes is observed at least out to the orbit of Saturn. So these are quite large-scale structures that you might imagine under certain circumstances could be detectable in systems around other stars. So these charged particles that are sourced from Io's lost volcanic gases then spread out throughout the system. Some of them deposit on the other moons in the system. And they also, when the electrons hit the atmospheres of the other moons in the system, they generate aurora. So these are actually images of Ganymede's aurora that are excited by these electrons that have come from Io. These are snapshots over a couple of hours. And Ganymede has auroral ovals kind of like the Earth. So you can see at the beginning that the southern auroral oval is lit up, and it transfers to the northern auroral oval over the course of this particular observation, which was made with high-res on Keck. In fact, these electrons come around and even excite aurora on Io itself. So these snapshots are now not as a function of time. These are all different wavelengths. And just Io has this whole slew of auroral lines at visible wavelengths, including the lines that we see on Earth, the red and green line, but many more of sulfur and oxygen and potassium and sodium. Okay, so these ions coming ultimately from Io's upper atmosphere are implanting on the other satellites. They're exciting aurora on all 4 of the satellites. They're also, as we've seen recently, driving winds on Io itself. So this is a completely different type of data. These are Doppler shift maps based on ULMA data of Io's 2 hemispheres. And so the top row, the 3 are just different dates or species. Don't worry too much about that. But the top row is the front hemisphere in Io's orbit. And what we see is that the gases in Io's atmosphere are all blue shifted on the front hemisphere, and they're all red shifted on the back or trailing hemisphere. So that's just, without even processing these in too much detail, you see the top row looks blue, the bottom row looks red. And that means that the winds in Io's atmosphere are always moving in Io's direction of motion, which is not what we expected to see. This is a paper that just came out in January of this year, and is the only thing that can produce that effect is the plasma, as far as we could come up with ideas. And specifically, once the material that's lost from Io or from any of the satellites becomes ionized, it now orbits Jupiter at the orbital rate of Jupiter's magnetic field, which is the rotational rate of Jupiter itself. That is about 10 hours, whereas the orbital periods of the satellites are in days. So that means that the plasma is always catching up to and overtaking the satellites. And so this plasma overtaking the satellites is, we think, somehow pushing the atmosphere and driving winds. Now it's, I have a little schematic here of that. So you have day to night sublimation flow, which is expected and that we also observe. And the torus, the plasma torus momentum is either adding to that or subtracting to it, depending on whether you're looking at the front or back hemisphere. So it's interesting that this effect would be observed, and I'd be curious to discuss with more atmospheres folks, specifically because the torus interaction should be happening at an altitude of a couple hundred kilometers or more, whereas the winds we observe are down at tens of kilometers. And so it's actually not obvious how you get that transfer of momentum from the upper atmosphere down to the deep atmosphere where we observe it. Okay, so moving on from this section, I'm just going to add to my list of open questions over time. The thing that I'm quite curious about in this case is, we see the mass loss, and I should have said this mass loss is occurring at a rate of about 1 to 3 tons per second. It's a pretty significant mass loss. And we see all these structures that are being generated over time, the mass loss rate, but as you have probably inferred from the way I've described it, there's some feedback here, where if you have more mass loss from Io, that's generating more ions and electrons. Since those are the things causing the mass loss, you have this positive feedback effect. So we kind of can see the state of the system now, but what is the history of the state of the system, and how has the sodium cloud and plasma environment structures changed over time? I think this is an important question from the perspective of just the next part of the talk that I'm about to get into, but also from the perspective of trying to look for a system like this around an exoplanet. How Io is now is just one data point, but what is the whole set of ways that it has potentially looked over its history as different parameters have changed? Okay, so what is the history of mass loss of Io? What is the history of tides at Io? We're starting to have a pretty good picture of how Io is today, although there are still all these open questions that I've listed. But we haven't had a lot of constraints on what it has been doing over time. In fact, models going back to Peel and Lee in 2002, numerical models, have shown that when you form the Jupiter system and the circumjovian disk, you capture the Galilean moons into resonance almost immediately, like on the time scale of 10 to the 4 to 10 to the 5 years. And so it's possible, and perhaps even likely, that Io, Europa, and Ganymede have been in this orbital resonance and therefore tidally heated for the entire age of the solar system. So as a kind of thought exercise motivated by this, you can think about how Io would have evolved over 4 billion years of tidal heating and volcanic activity. Specifically, we have this rate of 1 to 3 tons per second. You can multiply that out over 4 billion years and see how much mass you could have lost. But Io also has a pretty high resurfacing rate. So the actual solid material that's resurfacing, that's kind of extruding or being deposited onto the surface. And if you take that rate and you multiply that over the history of the solar system, you find that the amount of material that has to have come out onto Io's surface over the history of the solar system is tens to hundreds of times the entire volume of Io's mantle. And so people have postulated about recycling mechanisms. You obviously have to have a way to recycle that material back into the mantle and have it kind of come out again in the form of magma and outgassing. And this recycling process has to include the volatiles because they're still there. So they're recycling into the interior somehow too. So you may have this very chemically evolved moon. And yet, frustratingly, the surface, because it is so young, erases any real record of its long-term history. Mostly in the solar system, we can use cratering records to say something about the history of a planet and the relative timing of different things. Io has 0 to 1 impact craters. None had been detected until recently, and I saw a poster at an AGU meeting a couple of years ago where they had detected the first impact crater on Io, and that was very exciting. So how do you actually get any constraints on whether this process has been happening and how it has affected Io's chemistry and the chemistry of the object we see today? So we argue that we can do this using isotopes of sulfur. And in particular, coming back to this graphic I showed you before, the SO2 that comes out of Io's volcanoes, it forms the bulk SO2 atmosphere. Some of it freezes out and recycles back into the interior. But while it passes through the atmospheric reservoir, some of it is being lost, as I talked about in the last section. But which of it is being lost is important for this part. So when the SO2 is forming the bulk atmosphere, that bulk atmosphere becomes gravitationally stratified. So think about, for this example, the two most abundant isotopologues of SO2, which are the 32 SO2, the most common one, and the 34 SO2, which makes up roughly 5% in general. And so you can think about it like the scale height of the 32 SO2 is larger because it has a lower molecular mass. And therefore, as you go upwards in the atmosphere, the ratio of the 32 SO2 to the 34 SO2 is very slightly increasing. And so in the upper atmosphere where the mass loss is occurring, you're preferentially losing by a tiny amount the lighter SO2. Now, what remains in the bulk atmosphere, if it's not lost, eventually gets recycled back into the interior. And so you have this, that's what was shown in this little schematic here, this process of recycling and kind of incremental loss. And, on any given day or year or million years, the imprint of that loss on the reservoir is negligible. But if you actually multiply this out over 4 billion years, you can significantly enhance the heavy sulfur in Io's atmosphere. Now, if there are any geochemists in the audience, we did model this in quite some detail. I will not go into this for this particular talk, but we did in fact attempt to quantify all of the sulfur reservoirs on Io, the exchange rates between them, and how that would change the 34 to 32 sulfur isotope ratio. And Ari Hughes, who was formerly a postdoc at Caltech, wrote a really nice paper on that I would refer people to who are interested in the model. With that model in hand, we then went to make observations of Io's atmosphere. We do that with the Atacama Large Millimeter and Submillimeter Array, ALMA. And in fact, you already saw a product of ALMA data in the Doppler shift maps that I showed a few slides ago. But here's what the actual data look like from ALMA for Io. So these two rows are two different nights of observation, getting the two hemispheres, again, the leading and trailing. And each snapshot, each kind of postage stamp here is an image of Io in the gas lines from the labeled species. The dotted circle is the size of Io. So we observed the SO2 and SO in both the heavy and light isotopologues. We actually observed gaseous NaCl and KCl also with heavy and light isotopologues of chlorine. Just to tell you a little bit about what you're looking at. So the SO2 is basically an Io's bulk atmosphere, whereas the NaCl and KCl are only present in plumes. And so you see that they're isolated to these specific blobs. Those are probably volcanic plumes. To extract the isotope ratio, we do radiative transfer modeling. The free parameters in this case are the gas temperature and the column density for each species. And then you can take the ratios of the column densities for the two isotopologues to derive an isotope ratio. This is the number we derive. This is saying that the sulfur that we measure on Io is 36 plus or minus 9% heavier than the sulfur isotope ratio average in the solar system. So is that a lot? Is that a little? This is how that looks in the context of the solar system. So Io is substantially heavy in sulfur and actually also in chlorine, but we don't have a good model for chlorine at this point. But it supports the sulfur conclusions anyway. So it's heavier than anything else in the solar system, except maybe H2S on Hale-Bopp, but the uncertainties are quite large on that data point. So this supports this being a very evolved volatile reservoir where we've been losing mass for billions of years and enhancing the heavy sulfur in Io's atmosphere. But can we actually say something more quantitative than that? If you are willing to assume that Io's system is well approximated by a well-mixed system where continuous and incremental loss is occurring, then you can actually relate the sulfur isotope ratio that is observed today to the amount of the initial inventory of that element that still remains. The two things you have to assume are the initial isotope ratio and you have to believe that you know how much lighter the material is that's being lost than what's left behind. We calculate that from the complicated model that I showed you before. And if you run this equation on the measurement that we made, you get the result that Io has lost 94 to 99% of its available sulfur over its history. The word available in this case means it's the sulfur that is participating in this mixing and loss process, which we propose is all of the mantle, crust, and atmosphere reservoir, excluding what's in the core. And actually most of the sulfur is in the core, and it's not part of this process. So this seems like a high number, maybe even a suspiciously high number. Does it make sense? Actually, if you take Io's mass loss rate, its current mass loss rate, 1 to 3 tons per second, multiply it out over 4.5 billion years, you actually get basically the same result. You get a number that matches what we observe. So our measurement translates to Io having been losing mass on average 1/2 to 5 times its current rate for the age of the solar system. Our best fit measurement actually has Io losing mass at slightly above its current rate on average. So maybe there's some evidence for mass loss rates and even tidal heating rates being higher at earlier times. But basically, these numbers are all consistent with Io having been more or less the way it is for the history of the solar system. So we interpret this as saying that Io's been volcanically active, and therefore that the orbital resonance has existed between the moons for most or all of its history, maybe even with higher rates at earlier times. And this is quite consistent with the numerical models. There's a really nice correspondence here. Okay, so we'll wrap up here. I've added a couple other open questions to my list, and then I'll open it to discussion. So first, if Io's lost almost all of its SO2, what else has it lost? I told you it doesn't have H2O or CO2. Those are lighter than SO2. Did it once have water and lose the water because hydrogen is very light? And a kind of extrapolation from this question is the gradient in rock to ice ratio, where the rock to ice ratio decreases with distance from Jupiter, is that primordial and telling you something about the circumjovian disk, or is some portion of that a product of volatile loss, which would be an important constraint on models for the formation of satellites? All right, so I will close there. I'm going to leave this list of open questions up, and I'm happy to take questions or discuss. Thanks.
Thanks, Catherine, for the wonderful talk. Do we have any questions? Actually, maybe I'll ask the first one. Just like, so 99, so from what you said, 99% of the sulfur's been lost. So in the past, Io was born with way more sulfur than it has now. That's what your results are, right?
Correct. And again, like something like 80 to 90% of the sulfur is actually in the core. And so when I say 99%, it's 99% of the 10 to 20% that's not in the core. But
Sure.
yes.
Okay, so where was it? Was it in the mantle as like accessory sulfur phases, or what? Do you have any idea? That seems like a huge amount of rock to lose.
Of sulfur to lose. Yeah, no, it's a good question. And I would say, we don't really know the answer, but yes, as rock phases and as volatiles that are dissolved in the melt, so the SO2, when it gets our model, the way that our model treats the chemistry of sulfur is that the sulfur on the surface gets recycled into the interior, both in the form of basically SO2, which starts as frost, and then as you get deeper, it melts, and then it gets reincorporated kind of in that volatile state into the magma. But you also can have the chemical reactions forming sulfates between the silicates and the SO2, and those sulfates are stable to much deeper, and so you have at least these phases. But yeah, I would say we don't know the answer. If you have some ideas, I'd be curious to hear them.
Yeah. Okay. Lynn?
I think you're muted.
Just testing you. Thank you. I said thank you so much for a really great talk. I really enjoyed it. I was gonna ask kind of half jokingly, like on a scale from 0 to 10, how bitter are you about ESA juice not going to to IO? But I guess my more serious version of that question is there anything we can expect from ESA juice that could still help out in answering some of these questions? I don't know how like separate the sort of moon systems are from each other.
Yeah, so since I'm not involved in the JUICE mission, I don't have a good sense of what like specifically their capabilities are. I sure hope that they're going to look at IO. And I would say, there's a couple of things. One is that their particles and fields instruments are going to measure like all the particles that are filling the Jupiter system, or almost all of them, have come from Io. And so you're going to learn a lot about mass loss and about mass loading of the plasma torus and the neutral system. In my opinion, again, not knowing the specific capabilities of the instrument, I am most excited as extrapolation from the project that I just showed you most recently with the sulfur isotopes in the JUICE submillimeter wave instrument that making submillimeter observations. They had a press release where they showed some just spectacular data of Earth's upper atmosphere. They titled the press release like "Earth is a habitable planet." Or something along those lines. And I think that they should be capable of making measurements like I did, but also potentially of additional sulfur and oxygen isotopes. Again, I don't know for sure, but that would be the thing that I personally would be very excited to see come out of JUICE.
Yeah, little Alma flying by, basically. Yeah, actually, I don't know if there's like a flyby. Maybe I'm sure that it will come up in the path somewhere, right? So.
You can at least, I mean, spacecraft try very hard not to fly by Io because it's very dangerous for the instruments.
Yeah.
The high radiation environment. But you can do a lot from remote observation when remote is, so much closer than Earth.
Right.
So even observing from Io from Ganymede's orbit may give you some good information.
Yeah, it's really great. You've convinced me. I'm a fan. So thanks.
We have a question from Hannah.
Hi. Yeah, thanks for a great talk as well. I was wondering, kind of on point 5, we're asking if Io form with other volatiles. What is the residence time of species within that big torus around Jupiter? Like, could we expect to see some of those earlier volatiles still in that torus, or will they have been kind of stripped out by the solar wind?
We would not expect to see them there. I probably don't even know to order of magnitude for a given species what their residence time is, but I think it's like days, tens of days, hundreds of days, something like that, plus or minus an order of magnitude. It's definitely not approaching billions of years.
Thanks.
Unfortunately. But, I had thought about if you had those and they were lost, and then they implanted on the surface of Callisto, could they be hanging out on the surface of Callisto? But then how would you know whether those were volatiles that came from Io versus ones that were endogenic to Callisto? So I don't know.
I'll ask another question, actually. This sulfur recycling mechanism, do you have any guess of how generalizable that is to, for example, tidally heated exoplanets that are probably a lot more massive than Io?
Yeah, so I think that you could probably make a simplified version of this if you knew enough about the planet. So one key to this is that, well, I guess there's kind of the two keys. There's the recycling and there's the loss. You need a mechanism to recycle the volatiles. You could imagine that being different on different types of planets, but for Io, that works probably, at least in part, it's because you're close to the freezing temperature of SO2 or the sublimation temperature, so that allows the atmosphere to freeze out. But you would have this reaction producing sulfates even in the absence of that. And so, and then you could imagine if something actually had a liquid reservoir on the surface, that would give you quite a bit more extensive recycling mechanisms by chemical reactions between the liquids and the rock. And then the other is that you need a loss process, and you also need it to be fractionating. And so, in this case, we're losing a little bit of light stuff from the upper atmosphere. And so that is fractionating. However, in a mechanism like hydrodynamic escape, where you're losing, it's like a bulk loss process. I think the loss of the light material is driving the loss of the heavy material with it. And so that process will be nowhere near as preferencing of a specific isotope. So those are the two that you would need. Those are the two things you'd need kind of a story about to make a simple box model for an exoplanet like this.
Thanks. Any more questions for Katherine? I will take the liberty of actually asking a third one, if that's okay. I was really interested in this question of can tidal heating ever make a magma ocean? And I agree with your argument about making a subsurface magma ocean, just that the melt wants to go up and it will be hard to kind of keep it there. But if you could have a surface magma ocean, maybe because you didn't have like a vacuum above the planet, but maybe a bit of an atmosphere. Do you think that tidal heating could do that if it were high enough?
Yeah, I think, you know, if you can prevent, if you're either hot enough on the surface, either because your star is really close or because you have some like really pathological atmosphere, then yes, that seems plausible to me. And I'm not saying that you can't produce a magma ocean, a subsurface magma ocean from tides, but just that it's more complicated, right? Than just like there being enough heat. And you know, in the solar system, I had said on some slide that, you know, we don't have magma oceans in the solar system today, but we certainly did have them in the past. We had them, you know, on the surfaces of planets, and you know, you could even argue that they were in the subsurface during the phase when they were slowly cooling and crystallizing, and then you can generate a flotation crust of the crystallized material, and it's not fully cool in the subsurface. But that's not kind of a steady state magma ocean, I would say, is the difference. It's in the process of cooling. But yeah, I think that you could certainly have a parameter space in which you have a tidally generated, if the tides are high enough, surface magma ocean where somehow the surface temperature is preventing solidification at the top.
Yeah, that would be very cool for some exoplanet observers to try to find. Any final questions? Okay. In that case, let's all thank Katherine again for this fantastic talk about Io. And next month, we are going to have a talk from Lisa Dang on observing lava world exoplanets, and pay attention to the time change, which will be at 1400 UTC next month. Thank you all very much.